Before we talk about lithium-ion battery, now let's take a broader picture of what is an electrochemical energy storage device. Let's take a look at the definition. An electrochemical energy storage device is a setup that can convert chemical energy into electrical energy. So example given here are fuel cell, battery, supercap, and capacitor. So what is a fuel cell? A fuel cell basically is a device that can convert hydrogen and oxygen into water and electricity. So the active material are feed in externally. For example, like the hydrogen and oxygen, they are feed in into fuel cell from outside. The gas hydrogen undergo hydrogen oxidation reaction and it will form H+, which is a proton. So the hydrogen ion will transport across the membrane and electrochemically combine with oxygen to form water. At the same time, it will generate electricity. So in this case, you can see that the chemical energy stored in hydrogen and oxygen is being converted into electrical energy. So one important point to note is that the fuel cell is referred to have higher energy density as compared to the other energy storage device, for example, like batteries, like supercap and capacitor. However, fuel cell has a lower power as compared to the capacitor. So for application that require high power, for example, like camera, flashlight, we cannot use fuel cell, we have to use a capacitor. And other than hydrogen fuel cell, there is something called methane fuel cell as well. And the supercapacitor is a high capacity version of ordinary capacitor. So the main difference is that the supercapacitor is nanostructures and hence it can store more charge. And the supercapacitor and capacitor, they have higher power as compared to battery and fuel cell. So in this figure, you can see that it's very hard for a energy storage device to have high power and high energy at the same time. It's very difficult to achieve it. Usually, we will use capacity and voltage to describe electrochemical storage device, and we will look at this in the next slide. The theoretical cell voltage is defined as a chemical potential difference between cathode and anode. However, in practical application, the cell voltage will be lower due to the internal resistance. In other words, we can say that the cell voltage is related to the chemistry, or we say electrochemistry of the anode and the cathode. It is the difference between the cathode and anode that will form a cell potential. A capacity is defined as the amount of charge that a battery contains. It is the charge involved in the electrochemical reaction. The conventional unit is amp-hours or milliamp-hours. In the figure below, you can see that the capacity of the battery is 2000 milliamp-hours. So why the unit is amp-hours? Because we know that charge equals to current times time. So Q equals to IT. So this is the reason why we have amp-hours. Of course, this is not a standard unit. We say that the capacity is current rated or C rated. So what is the meaning of C rated? If a battery that has a high C, meaning to say that we charge the battery or discharge the battery very fast, the kinetic may not able to follow and there could be a breakdown of the battery structures or the energy will be lost as well. So usually we will charge a lithium battery at 1C or discharge a lithium battery at 1C. So what is the meaning of the C rating? So let's say the charging or discharging rate is 1C. It means it takes 1 hour to fully charge or fully discharge it, which is usually the case for lithium-ion battery. Let's say if the C rating is 2C, so it will take 30 minutes to fully charge or fully discharge the battery. So it has an inverse relationship with the time. So a high C takes a shorter time to charge and a low C takes a longer time to charge. However, this is just a theoretical concept. Usually we will just charge a lithium battery at 1C or less than that. Because if you charge it at a higher C, it cannot catch up kinetically and this could destroy the lithium-ion battery. If you discharge your battery very slow, then the lithium ion can diffuse out very slowly and nicely from the electrode matrix. However, if you discharge your battery very fast, then the lithium ion cannot come up from the matrix, the electrode matrix, very nicely. And this could result in a loss of capacity because not all the lithium ion can come up from it. And of course, the energy of the battery will be lost as heat as well. So we can see over here that the capacity is C rated as well as the energy is C rated. Energy is defined by voltage times the charge, and it can be integrated from the VC curve, underneath the VC curve. The conventional unit is watts time hour or volt time ampere time hours. So where the watts come from? Watts actually is the unit of power. So we know that energy equals to power times times. So we have watts times power. And we also can have something called energy density. Basically, we will try to normalize the energy by using the volume or the weight. Energy is like how much of water contained in a basket, and then power is like how fast can you withdraw the water from the basket. Sometimes you need to know what is begin normalized. Is the whole electrode begin normalized or the active material only? So you need to clarify which is the normalized factor. Let's take a look at the exercise, calculation of energy density. So questions. A battery with a nominal capacity of 2600 milliamp hour and a nominal potential of 3.7 volts with a total mass of 46 gram. What is the energy density? The nominal voltage is a voltage given by the manufacturer. The actual voltage of a cell will usually vary around this nominal value. For example, if a battery has a nominal voltage of 3.7 volts, the actual voltage is somewhere in between 2.8 volts to 4.2 volts. This is the typical lithium-ion battery for lithium cobalt oxide as the cathode and graphite as the anode, which is the first commercialized lithium-ion battery developed by Sony company in 1991. So the answer will be, according to the definition of energy density, it will be the voltage times capacity divided by mass. So as we plug in all the number, and we will get the value. Let's take a look at another exercise, balancing capacity between anode and cathode. So a lithium-ion battery consists of lithium titanium oxide and lithium iron phosphate as the anode and cathode respectively. What are the required mass of the cathode and anode to achieve a theoretical capacity of 170 amp hours? It's given that the specific capacity of the lithium iron phosphate and lithium titanium oxide are 170 and 175 amp hour per kilogram. You can pause the video for a second, for a few minutes, and then try to do the exercise before I go through with you. Alright, let's take a look at the answer. So basically, we just need to compare the amount of ratios. 170 as compared to 175 in terms of the theoretical capacity. So after that, by dividing 170 to both number, we can get 1 to 0.97. So to construct the required capacity of the lithium-ion battery, we need 1 kg of lithium iron phosphate and 0.797 kilogram of lithium titanium oxide. So why do we need to balance the capacity between the cathode and anode? That's because, for example, that the graphite, which is the anode, when fully charged, all the sides are occupied by the lithium ions. However, you still have excessive lithium to be delivered to the graphite, which is the anode, and this will cause plating of the lithium ion and also cause the formation of dendrite, which is very bad for the battery. The formation of dendrite will cause thermal runaway and will cause fire, will possibly cause fire to the lithium-ion battery, which we'll talk about later. Just bear in mind that the anode and cathode need to be balanced, like more or less the same. We now talk about primary battery and secondary batteries. So primary batteries are single-use and disposable battery, and that's because the chemical reactions, or we say the electrochemical reaction, are irreversible. So primary battery, they are not rechargeable, however, they are low cost. Example of primary cell include zinc carbon battery, alkaline cell, silver oxide cell, and mercury cell, which is banned now. The alkaline cell is an improved version of the Leclancher cell. The major difference is the improve of the electrolyte in the alkaline cell. That is, it use the aqueous KOH, potassium hydroxide, and this is where the name come from, alkaline. And also, alkaline cell use porous zinc instead of solid zinc as the negative electrode. So because the alkaline cell use a porous zinc as an electrode, it has a higher specific energy, in about 20 to 30% higher than the zinc carbon battery, which is the Leclancher cells. And then we have a silver oxide cell. It has a high energy to weight ratio with about 40% longer runtime than the lithium-ion batteries. So it can be used for watch or some military devices. However, the disadvantage is that silver oxide cell is more expensive because it has the raw element which is silver in it. And then now we take a look at the secondary battery, which is designed to be able to charge and discharge continuously. Original composition of the electrode material can be restored by reverse current up to a certain number of cycles before the side reaction become very significant, before the secondary battery loss its reversibility. One of the famous example is lead acid battery, which come in 2.1 volts in the unit cell. So it means that you can have a battery with an even number of the volts. So the most common volts are 2 volt, 6 volt, 12 volt, and 24 volts. The car lead acid battery is typically 12 volts. And we have a nickel cadmium battery. Nickel cadmium battery is toxic because of the element cadmium, and it is also notorious for the memory effect. A nickel cadmium battery could remember how much energy was charged on the previous cycle, and it would not deliver more than it was demanded before. The nickel metal hydride cell has been developed from the nickel cadmium cells, and the nickel metal hydride battery can have 2 or 3 times the capacity of nickel cadmium battery of the same size. However, both lithium cadmium and lithium metal hydride cells has a lower energy density as compared to the lithium ion battery. Last but not least, we have lithium ion batteries. The lithium ion battery has no memory effect, so it doesn't matter when you first use the battery, you fully charge it or not. In this figure, you can see that the figure metric of primary and the secondary cells. One interesting phenomenon or one interesting observation is that you can see that not all the cathodes are in solid phase. Some of them can be in a gas phase, for example like zinc air battery. Another point to note is that primary cell or secondary cells that use lithium as the anode has a higher cell voltage. So why is that so? We will talk about this in the next sharing. And most of the primary cell and secondary cells are not commonly seen in our daily life. They are still in the research phase. Now here's come to our last slide before we go to the summary. So this is a figure of metric for secondary battery, for rechargeable battery. So we have lithium ion battery that has higher energy density as compared to the nickel metal hydride and nickel cadmium. And this PLiON is lithium polymer battery, which use polymer as the electrolyte instead of liquid electrolyte. So most of the time, we do not use metallic lithium as the anode of lithium-ion battery because the formation of dendrite can easily protrude the lithium-ion membrane and cause thermal runaway. Although lead-acid battery has the lowest energy density, it is less sensitive to temperature and it has less safety concern, and therefore it can be used for our car, and it doesn't cause any problem during winter and summer as compared to the lithium-ion battery. So here come to the summary of part 1. We talk about the fundamental knowledge of lithium-ion battery, or we say the background of lithium-ion battery. We cover the concept of electrochemical energy storage devices, and we say that the main trade-off of these devices are between the power and the energy. So energy storage can have either higher power or high energy, but not both. We also mentioned that the fuel cell has the highest energy density, but lowest power density, while the capacitor has the highest power density, but lowest energy density. And the supercap and the batteries bridge across these two cell technologies. We also cover the concept of voltage and capacity. So the cell voltage of a battery depends on the difference of the potential in the cathode and anode, and the potential of the electrodes depends on the electrochemistry. However, one should bear in mind that the practical cell voltage will be lower due to the IR loss. The capacity of an energy storage device depends on the charge that it can store during the electrochemical reactions. And we also mentioned that the capacity is C rate dependent. With a higher C rate, you can store a little amount of the capacity. And then the energy is defined by the multiplication of the voltage and capacity. Since the capacity is C rate dependent, the energy also is C rate dependent as well. In fact, the voltage of the cell will also drop significantly if we are running the battery at a high discharge rate, high C rate. So the energy is a function of the C rate as well. We also give the analogy that the energy is like how much of water can be contained in a basket, and the power is how fast you can withdraw the water, is the water flow. Both energy and the power can be normalized by the volume or the mass, which give rise to volumetric energy density or power density, and also gravimetric energy density and power density. However, when you read the energy density or power density from a manufacturer, you need to ask a question whether this normalization is based on the active material or the whole electrode, because an electrode may consist active material and also binder, so the energy density or the power density will be lost. We also cover what is battery. A battery can be categorized in a primary battery and secondary battery based on the rechargeability. And a secondary battery can be recharged and then can be reused and is more sustainable. So lithium-ion battery fall into the secondary batteries. Last but not least, we talk about the figure of matrix. So we find that the electron material that use lithium as the electrode has a wider cell potential. And we also mentioned that the electrode may not necessarily be a solid phase. It can be in a gas phase, for example, like the lithium air battery or zinc air battery. And we also mentioned that the lithium-ion battery has a higher energy density as compared to the nickel cadmium and nickel metal hydrate. So that's all for the chapter 1.